For this reaction, we've got bromate, and 5 bromides and hydrogen. So this is obviously, one of those redox ones taking place in acidic solution, as you can see. We've got 3 reactants, though, that we need to figure out what their order of their reactant is in the rate law. So the general form for this, of course, is going to be the rate equals the rate constant K times the concentration of the first reactant, which is bromate, raised to its order of reactant, which we don't know, N, times the concentration of the bromide raised to its order of reactant, which we don't know, and then the hydrogen reactant raised to its order of reactant. In this case, we're using generalized P here. Now remember, these order of reactants, the N, M, and P, have nothing to do with the balanced reaction. We have to look at the experimental data. And how does the experimental data look for these problems? This is how it looks. They're going to give you charts like this, where you have initial concentrations, and then you have the rates over to the side. This is that initial rate method where this is like experiment 1, this is experiment 2, experiment 3, and experiment 4. So this experiment, or this reaction, was run 4 different times with 4 different initial concentrations, and then they ended up obtaining and measuring the initial rate for each experiment. Now we're going to do each individual reactant separately, but I'm going to do the long way for bromate, the first one, so you can see the full detail as to where I'm getting this information from, or how I'm putting it into the equation. So let's start with bromate. And I'm going to go ahead and put the, the generalized rate law here at the bottom that we're going to use. So the rate equals K times the bromate raised to the N times the bromide raised to the M, and then the hydrogen here raised to the P, those order of reactants. That's the generalized rate law we will be using. When you're deciding, we're going to figure them out individually. So we're going to start here with the first reactant, the bromate. We're using the blue there. Now what you need to look at is in the experiments. You want to look at the experiments and find 2 experiments where bromate is the only concentration that's changing. You want bromide and hydrogen's concentrations to remain the same. So which 2 experiments up there is where bromate is the only thing changing that I can use to calculate with? Which 2 is where only the bromate concentrations are changing, not the bromide or the hydrogen? Which 2 experiments do I need to choose? One and 2, very good. So that's what I select here. I'm going to do 1 and 2 for my bromate. Okay. Now, basically, I always put the one with the higher concentration on top. I mean, you can do it the other way, but it's a little bit different in terms of the math. So I'm going to put experiment 2 on the top and experiment 1 on the bottom. All right, and we're going to be following this format of this overall equation. So the rate here for experiment 2 is going to be 1.6 times 10 to the minus 3. That's going to be over the rate of experiment 1, which is 8 times 10 to the minus 4. Okay, so we're taking both experiments and using their information about their rates, their rate law here. Now that's going to be K over K for both, because the first experiment's going to have a rate constant. The bottom experiment obviously will have the same rate constant. Now we're going to plug in the concentrations for bromate. So 0.2, and we're going to raise this to the N. This is over 0.1 raised to the N. So those 2 have been filled in. Now technically, we would, I just want to show you like where we're going with this, and then I'll show you how to condense it down. So the bromide coming next would be 0.1 raised to the m over 0.1 raised to the m. And then, so those two, and then these two for the hydrogen, 0.1 raised to the p over 0.1 raised to the p. So this would be like writing it all out and using that construct of the rate law down below. However, as you'll notice, these guys cancel because they are the exact same thing. These guys cancel as well. The k's cancel. We don't really need to put them in there. So really all we need is the rate and the concentrations with their raised to their order of reactant. The other stuff you don't really need in order to figure out the order of reactant. Now, one thing to notice here, for math purposes and calculator purposes, I'm going to show you how they do it for kinetics, and this is where they expect you to be able to do the mental math. You take this, you move it over 1 this way, that makes this a -4. So now it's technically 16 divided by 8, because it's 16 times 10 to the -4 divided by 8 times 10 to the -4. So what is that value going to be there for the 16 divided by 8? It looks like complex numbers, but it really isn't. Because 16 divided by 8 is what? It's 2. The 10 to the 4s cancel out too, right? They cancel, so now we're just got 2. And then we have the 0.2 divided by 0.1 raised to the n. So what is 0.2 divided by 0.1? .2 divided by 0.1, that's 2, right? Raised to the n there, like so. Yeah, so now 2 equals 2 to the n. What is n going to be then? N equals a 1, because 2 to the first power equals 2. Does everybody see that? So technically this n now we figured out is a first order reactant. It's a 1. So now let's look at bromide. We'll do bromide in green. We need to pick 2 experiments for bromide where only bromide is changing, not the hydrogen, not the bromate. So what 2 experiments is where the bromide is changing, but the other 2 are staying and remaining the same? So look at your data. Where is it showing bromate and hydrogen stay the same concentrations, but the bromide, the Br minus, is the only one where the concentration changes? Yes, it's 2 and 3. So I'm going to use experiments 2 and 3. Once again, putting the larger one on the, or the one with the larger values on the top. So 2 and 3, we're going to be using these. Experiment 2. Now, rate 3.2 times 10 to the minus 3 over the other rate, 1.6 times 10 to the minus 3. That's going to equal the 0.02 raised to the m over the 0.01 raised to the m. Once again, we're not going to include the other things because we don't need them. Because the bromates aren't changing, the hydrogen's not changing, we don't need to include them. We don't need to include the K's, they cancel anyways. So if we look at this math now, this is basically 3.2 times 10 to the minus 3 divided by 1.6 times 10 to the minus 3. What is that going to be? As you can see, they're pretty easy numbers. So that one should be 3.2 divided by 1.6 is really like 32 divided by 16. If you move them up both the same decimal over, it ends up dividing the same. So what do we get here for this side, the rate side, this part? The 10 to the minus 3's cancel, 3.2 divided by 1.6, that should give you a 2. 0.2 divided by 0.1, once again, is 2 raised to the m. So what is our order of reactant for M then? M equals 1 also, because 2 to the first power equals 2. So that's what this one's going to be. This one's going to be a 1 as well. So bromate and bromide are both first order reactants. That means you change the concentration, or you alter the concentration, that same factor will be have that effect on the rate as well. For the last one, let's look at hydrogen here. All right, I'm going to do hydrogen in the black. We need 2 experiments where only hydrogen is changing and the other ones are not the bromate or the bromide. So which 2 experiments do I need to use? Where is only the hydrogens changing and the other 2 reactant concentrations are remaining the same? 1 and 4, good. So once again, I'm going to put 4 on the top because it has the larger concentration value over experiment 1 on the bottom. So yes, we're going to do 1 and 4. So the rate here, 3.2 times 10 to the minus 3 over 8 times 10 to the minus 4. Okay, so this is going to be 0.2 raised to the p over 0.1 raised to the p. And they shouldn't be, terribly difficult numbers to deal with. Now, once again, showing here, you can move this over here, so make it 32 times 10 to the minus 4. That means the minus 4's cancel, and it's really 32 divided by 8. It's just playing around with those, exponent rules. So 32 divided by 8 is going to give you 4. 0.2 divided by 0.1 again is 2. So in this case, what is the value of the exponent for the p there? It's going to be a 2. So p is going to be 2 here. So this order of the reactant is now a 2. So we have first order for bromate, we have first order for bromide, and we have second order for hydrogen. Very good. So technically, if I rewrote this nicely, how it would look, it would be rate equals K times the concentration of the bromate times the concentration of the bromide. You don't have to put the ones in because, technically it's understood. And then hydrogen, you put the 2 over like that. Now, I know it doesn't ask for it, but what's the overall order for this entire reaction? What's the overall order? What does that equal to? How do we figure that out again? What's the overall order for this reaction? Because we're going to need that actually later in just a second. It's 4, good. Because all you have to do is add the 1 plus the 1 plus the 2. So this is an overall order of 4. Very good. Now, so far so good. We need to calculate for K. That's another thing that we need to do. I'll rewrite it up here so we have it. Rate equals K times the bromate times the bromide times the hydrogen squared. All right, to find K, all you have to do is pick an experiment. It really doesn't matter which one. Let's say we want to use experiment 2. We just use these numbers and plug them in, the concentrations and the rate. So this would be 1.6 times 10 to the minus 3 molar per second equals K times 0.2 times bromide 0.1 and then times the hydrogen 0.1 squared. Now all we have to do, multiply and divide. So what do you get for your number for K? Let's go ahead and calculate that. 1.6 times 10 to the minus 3 divided by 0.2 divided by 0.1 divided by 0.1 squared. So what do we get for our K? Calculating the K. K equals, oh, that kind of looks like an uppercase K. I'm going to write it smaller. So we don't get rate constant K confused with equilibrium K. So what's our number here? What's the rate constant? What's the rate constant? Come on. Somebody calculate it. Anyone? Come on, guys. You can do this. Come on, folks. Yay! Okay, so people got it. Good. It's 8 or 8.0. I would go with 8.0 because all of these have 2 digits in them. Okay. 8.0. Now, the complicated part is the K units. They always ask about the K units, and the K units are always like 1 point of the test. So you don't want to mess up the K units. Now let me explain where the K units come from. This is like M, this is like M, and this is like M squared, right? So really, over here on this side, we have molar per second, and then on this side, we're going to be dividing by molar times molar times molar squared. It really doesn't matter. Okay, so that's a good question. Going back to where did, we just chose one. It doesn't matter which experiment you use. You can use any of those. I just chose to use 2. You could use 4, you're still going to get 8. You could use number 1, the experiment 1, and that will also give you 8. So you just choose one of them, and then you can plug in to find K. So that's a good one here. All right, so back to K, calculating K units here. We really technically molar times molar times molar squared over here. So really we're dividing over here. Molar per second is being divided also on over here on this side. It's a terrible division sign, but divided by molar times molar times molar squared, which is really m to the 4th, right? So technically this looks like this. It's going to be m over the second times molar to the 4th. So this cancels, and what we end up with is 1 over, and technically you write the molar first, it'd be m to the 3rd times the 2nd. So the K units end up being 1 over m to the 3rd times s, because our time unit is seconds here. That's pretty complicated to think about and try to cancel all of that down. So I'm going to give you a shortcut to finding the K units without having to do all that canceling and modifying. You can use this equation here, because those rate constant units are very important. They always ask for always have a point on there. And you must have units for your K, or they'll take off that 1 point. Usually it's 1 point for the number and 1 point for the units. If you look at the free response scoring guidelines. You can use this formula and memorize it, and then it makes it a whole lot easier. You just do N as the overall reaction order, and we know that the overall reaction order that we had was 4. So all you'd have to do is 1 over m to the 4 minus 1 times the time, and we knew it was seconds. So this is going to be 1 over m to the 3 times that. So you could also write it, or you might see it written like to the minus 3, s to the minus 1, like that. Sometimes they like to use that kind of notation as well, showing that it's on the bottom of the fraction. But that's what you need to do. Units for K are important. Make sure that you always have those in there when you're calculating a K. Any questions on that?